Okay, so we continue with the divergence theorem, and I think this will be the last example on the divergence theorem. Again, it's a standard procedure, but I will take this time my surface be the cone, z equals root x squared plus y squared, z between let's say 0 and 1, and including its top. Compute surface integral f dot n dA for the function. Let's choose a function. And this time, I want my function to be not that easy to compute. For example, y squared over y to the 4 plus 1 plus x cubed tan squared x over z squared plus x squared plus 1 minus y and z. Again, with these examples, we feel how the divergence theorem is really useful. Because if we think to compute this integral without using the divergence theorem, we can see these quantities y squared, y to the 4 plus 1. I added them intentionally just to show you how the divergence theorem simplifies, in some cases, simplifies the computations. So although the divergence theorem gives us a triple integral, and I know some students are scared when they hear triple integrals, but the triple integrals in any way are much easier than dealing with these quantities with the parameterization. And let me, in the same question, I will say n being the outward normal vector. Okay? Okay, so in this example, my surface is the cone, z equals root x squared plus y squared. This is it. Z is from 0 to 1, and I'm telling you that take it with its top. So the top is included, and please notice that the top equation is not z equals x squared plus y squared with the root. It is x squared plus y squared less than or equal to 1. And this is the cone equation. So this is my surface. Now simply, this is a closed surface. The normal vector is the outward normal vector. So we can apply the divergence theorem. So what does the divergence theorem say? Simply, you take the integral equals the triple integral of divergence of dv. And remember, please, what is the t? The t is the solid. This is the t. It's the solid inside your surface. It is the solid. It's the volume inside your surface. So it's not the surface itself, but it's the region inside that surface. It's a 3D region. Okay, so now you start computing this integral. Now what's the divergence? So here we see the significance of the divergence theorem in this example. So you differentiate the first component. This is the first component of the function. You differentiate it with respect to x. So everything in terms of y gets cancelled. The second coordinate differentiates with respect to y, the third with respect to z. And I'm going to say this is my solid of integration. Okay, so the one is cancelled. And this is my integral. So I need to integrate 3x squared dv over this cone. How do we integrate this? Of course, as a triple integral, I can do it as dx, dy, dz. That's completely right. I can do it using spherical coordinates. I can do it using cylindrical coordinates. So my goal in this example is to show you the three computations, okay? So what is, first of all, what is the best way to compute this integral? For the cone, the best thing is spherical coordinates. And you will see why. The spherical coordinates is absolutely the best thing to use in computing triple integrals over the cone. So let's see why triple integrals over cones are best with spherical coordinates. This is my cone again. The axis. Okay, remember, in spherical coordinates, what's the x? The x is rho sine phi cosine theta. This is a square. What's the dv? It's rho square sine phi d rho d theta d phi. So these are the integrals, everything inside the integral. Remember, this rho square sine phi d rho d theta d phi, this is the replacement of dv. So in general, whenever you have a triple integral with dv, what's the dv? The dv is dx, dy, dz, of course in any order. If you want to replace that, to change the integral to a spherical coordinates, then the dv must be replaced with rho square sine phi d rho d theta d phi. That's a rule. Okay. Now what is like the most difficult thing in converting integrals from dx, dy, dz to spherical coordinates? And in general, what's the most difficult thing in computations of triple integrals? I think it is writing the limits of the integral. After writing the limits, the integral itself is not a big deal. The integral can be done using the well-known integration techniques. And again, this is not a Calculus 2 course. We're not testing you in integrals, techniques of integration. We're testing the ideas of this course. Okay, so now I want to show you how to write the limits. First, all the time, you start with the outer variable, which is theta. Remember, what is the meaning of theta? Theta means you look at your solid. So this is your region. Imagine you take all points inside this cone. This is your solid of integration. And you want to say, what is the theta corresponding to these points? So if you agree, some points lie on the positive z-axis. Some points are here, right? So for those points, what is the phi? Remember, the phi is the angle made with the positive z-axis, so the phi is 0. But then, if you take a point here, for example, or here, or here, or there, then you have a bigger phi, and as you move this way, you have a bigger phi, and imagine, now we are drawing in R2, but my cone is in R3, so we are doing this in all possible directions in R3. So imagine, you start with the positive z-axis and you keep moving until you hit the cone. So if you agree, the maximum value for phi comes from the cone. Here is the maximum value for phi. So the question is, what is the maximum value for phi? What is the phi? What is the phi that corresponds to points on the cone? So going back to the cone equation, the cone equation is z equals root x squared plus y squared. Let's analyze this a little, and we can do it here. Just some analysis of z. So z equals root x squared plus y squared. We are dealing with spherical coordinates. So in this case, what is the z? The z is rho cosine phi. What is root x squared plus y squared? This is r. R is not among the spherical coordinates, so I need to change it. What is r in terms of the spherical coordinates? It's rho sine phi. So basically, if you cancel the rho, and here we need to observe that the rho can be 0, yes. If you are at the origin, the rho can be 0. But if you ignore the origin, so you have basically cosine phi on the cone, except for the origin. Cosine phi equals sine phi. What is that phi? You have the upward cone, and you have this phi between 0 and pi. Remember, the phi values are only between 0 and pi, such that cosine phi is equal to sine phi. That means the phi is pi over 4. So what we are saying is that if you take any point on the cone, if you take any point here on the cone, the phi will be pi over 4. This means the phi limits are from 0 to pi over 4. So this is how we find the phi limits in this example. Now what about the theta limits? Now the theta limits, imagine you take any phi. Imagine you take any phi. Okay, so for example, I'm drawing another one here. So this is your z-axis. Okay. So imagine you take a point here with a certain phi, and of course this phi corresponds, if you agree, to a complete cone like this. So all points on this little cone have the same value for phi. Now for those points having the same value for phi, what are the theta values? What is the meaning of the theta values? The theta values mean, if you take all these points having the same phi values, you project them down, you take them down to the xy plane. What do you get? You will get a disk. For this disk, what are the theta values? They are from 0 to 2 pi again. Now after doing this, what are the rho values? The rho value is the distance from the origin. So if you take any point inside this cone and you ask, okay, these points, what is, for these points, what is the least rho value? What is the highest rho value? Now it is clear to us. It is very clear. We need a new color. If you take any point, so you will go from the origin this way, you keep moving until you hit this disk. In any direction, you keep moving this way until you hit what? The disk. So basically, what is the rho? So the maximum value for rho comes from here. The maximum value for rho, when you hit the disk, which is the cone top, you get the maximum value for rho. So the minimum value for rho is 0, because you start at the origin from in all directions. But what about the maximum value? For the maximum value, again, I'm doing it here. So maybe this is the most difficult thing in these computations. So the maximum value for rho comes from the top. What's the top equation? The top equation is z equals 1. But what is the z in terms of the rho? The z is rho cosine phi. That's equal to 1. So what is rho when z is equal to 1? It's 1 over cosine, which is secant phi. So now we say, okay, so the rho goes from the origin. It keeps increasing until you hit what? The top. And on the top, what's the rho? It's secant phi. So these are the limits. Now these are the limits. So this is my triple integral. After this, it's just standard computation. So I'm not wasting any time on computing this integral. Okay, so let's go back to the idea. Let's not forget the idea of the example. The idea of the example was to show you two things. First, the significance of the divergence theorem. What do I mean by significance? I mean, if you look at this function, it looks really complicated. Y square, y to the 4 plus 1, tan square, and so on. But after finding the divergence of this function, we are left with a 3x square, which is much easier than the original quantities. So this was the first target of this example. The second thing, I wanted to show you how to deal with the limits of the triple integral in case you have a cone. So I did it using spherical coordinates. That's completely fine. And again, the easiest coordinates with the cone are the spherical coordinates. Now, what about, let's compute the same integral. Let's write the limits of the integral. In case you like to use cylindrical coordinates. Remember, what do we mean by cylindrical coordinates? Basically and simply, these are polar coordinates, but in R3. So what are the polar coordinates? The axes are cosine, the y's are sine, the z is z. That's it. Okay? So now what's my integrand? My integrand was 3x squared, 3x in terms of polar coordinates squared. That's it. What is the dv? The dv is dz dx dy, but the dx dy is r dr d theta. So this thing, sorry, comes from dx dy, okay? And this is my region. We are integrating again over the cone. So this becomes the triple integral 3 r cubed cosine squared theta dz dr d theta. So this is my integrand. Now what about the limits? The theta again, because you are dealing with the cone, the theta, you are making a full rotation about the z-axis. So this is from 0 to 2 pi. What about the r values? Now for theta and r values, all the time, okay, all the time, you are dealing with a triple integral. You take your cone, your region of integration, and you project it down all the time. R and theta are found from the xy plane. So this is the x, this is the y. If you project, what do you mean by project? If you take all points, imagine these infinitely many points inside the cone, take them down to the xy plane, what do you get? You will get exactly this thing. This region here will go down there. So it's a disk. And we already know that the disk radius is 1. So the r values are from 0 to 1. Now once you finish taking r and theta, you need the z values. How do you find the z values? When you take theta between 0 to pi, so these are the theta values from 0 to 2 pi, you are rotating this way. And the r from 0 to 1. So you already covered this disk down on the bottom. Now after taking these values on the bottom, you want the z value. So you say, okay, for each of these points on this disk, what is the minimum z value? What is the maximum z value? So when you go up, if you agree, so you have this bottom down, and you have the cone above it. And remember, your region is not this. This is not your region. It's not this. Your region is the cone, what's inside the cone. So when you go up from the disk down on the xy plane, you're not counting this area. So all of this is empty. So you start counting when you exactly reach the cone. So this is the minimum value for z when you reach the cone, and then you go up until you hit the top. This is not included. You start counting when you reach the cone until you hit the top. So if you agree the minimum value for z is exactly here on the cone, so this is the minimum value for z. But what is z there? Z on the cone is root x squared plus y squared, which is what? Which is r. So the minimum value for z is r, and the maximum value for z is when you reach here, the top, which is when these are the limits. So this is how we write the limits in case we want to use the cylindrical coordinates with the cone. Then lastly, I want to show you, then of course these are just computations and you will get the same answer as from the spherical coordinates. Now I want to show you what happens if you want to use what? The rectangular coordinates. So now I'm using the x, y, z, and we will see that the x, y, z is the worst choice, then the cylindrical, then the best choice is the spherical coordinates. So now I'm writing the integral of 3x squared dz dy dx. I'm using the Cartesian or the rectangular coordinates. Okay, so remember, if you have a triple integral, dz dy dx, how do we write the limits? The first thing, you take your solid of integration, you project it to the outer limits. You project it to the plane of the outer variables. So now you say, okay, that's my cone, project it down to the xy plane. What do you get? We know it. It's a disk, like this. What is the equation of this circle? It's x squared plus y squared equals 1. Okay, so now you start writing the limits of x and y. For the x limits, because the radius is 1, the x limits are from -1 to 1. Now we are done with the x limits. After doing the x limits, so for each of the x values, what is the minimum y value? What is the maximum y value? It's not from -1 to 1. It's from the lower semicircle to the upper semicircle. Please, this is a circle, okay? I did it quickly, but this is a circle. So now we ask, okay, what is the equation of the lower semicircle? I want it in terms of y. So if you look at the equation x squared plus y squared equals 1, what is y? Y down is negative 1 minus x squared, and y up is positive 1 minus x squared. So the y limits are from negative root 1 minus x squared to the positive root 1 minus x squared. Now we are done with the x and y. After finishing the x and y, so we did this region. Now we need to go back to the cone to find the z values. So this is my cone. What we finished is this projection down. We finished this. Now I want the z values. How do you find the z values? Again, you go up in the z direction. This is empty. This is not included in your region. Your region starts exactly at the cone. So what is the z on your cone? The z equation is root x squared plus y squared. Then, after hitting the cone, you go up until you get the top of your cone, and on the top, z is equal to 1. So these are the limits in case you are using the x, y, z. Now, I'm sure everybody's seeing these integrals, the three integrals. This is the spherical integral, this is the cylindrical integral, and this is the rectangular integral. It is clear that the cylindrical and spherical are computing on the easiest. Usually the spherical is easier than the cylindrical coordinates, and the reason is because the cone equation is very simple in spherical coordinates. It's phi equals pi over 4. It's your choice, of course, to choose which coordinates. Again, this is not a calculus course. We're not very concerned with the computations, but you need to know how to compute these integrals. So I'm leaving it for you to compute the three integrals and be assured to have this